Hello, stats class. Here's lesson 7.1c, which is more about sampling distribution. So we're wrapping up that lesson that basically the book's title is, What is a Sampling Distribution? So I hope that we've got this already, this definition, but I'm going to write it one more time just in case. Make sure you say sampling and not sample, because that makes a difference. Sampling distribution officially is the distribution of many statistics and I'm going to put the picky definition this time, which is not just from many random samples, but specifically if you want it to be complete, you would do from all possible random samples of a given size called n from a given population. So whatever your population is, you decide what sample size you're going to use. You take a sample of that size, you calculate your statistic, you do it again, calculate another statistic from your second sample, you do it again, you do it again, you keep doing it for every possible random sample. When it says all possible, that's the exact version. That means that you have a full, complete sampling distribution, but most of the time we do an approximate sampling distribution, which is many random samples, but not all. We're going to usually do this version in this class. So, step by step, what do you do to make this happen? Sometimes this helps people to see what the steps are. So, you start by taking a sample, usually random sample. All right, you calculate something. You might find the mean, you might find a proportion, you might find the maximum, any of those things that we talked about before. That's something that you calculate is called a statistic. You repeat it many, many times. And you graph it. Or sometimes you just describe the shape, center, spread, something like that. But that collection of all those statistics, whoa, I spelled describe wrong, that's an E. That collection of all the statistics is a sampling distribution. And that's different from the distribution of a specific sample, as we talked about before. All right, so that's kind of summarizing the most important thing for this week, which is what is it and how do you do it? And then today we're going to start talking about the center and spread, not so much the shape yet, that's coming later, but what happens with the center and spread of a sampling distribution. So the center depends on whether you've got a biased estimator or an unbiased estimator, and let's talk about that. That estimator is the statistic that you are calculating. So a statistic is used as an estimator if it's used to estimate the parameter, and if it's biased, that means it tends to be too high or too low. And we saw some of these in the warm-up. I can't remember if it was the warm-up that goes with this lesson or if it was 7.1b, but regardless, we saw some that tended to not work very well. For example, the range. If you take the range of your sample, well, the sample probably doesn't go all the way from the smallest population value to the largest population value, so that range is going to be too small. So the population might have this range and the sample would have a smaller range. Same thing happens with the max. the maximum of your sample is probably lower than the maximum of your population. So both of these tend to be too low and they are biased, which is why max would not be a good choice for the German tanks example. And I asked you to explain that in the Desmos. Minimum goes the other way. The minimum of your population is probably smaller than the minimum of your sample, unless you happen to get that smallest value in your sample. And so the min tends to be too high to estimate the population minimum. So there's some examples of naturally biased estimators, which is why we don't use those very much, because they're biased. Unbiased means that the mean of all the statistics, or the mean of the sampling distribution, is the same as the parameter you are trying to estimate. In other words, all those different statistics from different samples, some come out too high, some come out too low, but they average right around what you want to estimate. And this happens naturally with the two most common ones that I'd already told you about. The mean of X bar, which is the mean of all the sample means, is the same as mu, or the same as the mean of the population. And that equation being true means that X bar is an unbiased estimator of mu. So I wrote that as a sentence on purpose because I want to make sure that you're clear on what it is that's estimating what. We're using a sample mean to estimate a population mean, and the reason it works is that if you do all the possible sample means, it's possible to prove that the mean of all those is the same as the population mean. So that's like 3 different means in one sentence, and I apologize. This is the sample mean. There's a lot of them from different samples. This is the population mean. This is the mean of all the sample means, and it matches, and that's good. That's one of the reasons why mean is a common one to be done. When I went to graduate school, I learned how to prove that this is true. You do not have to prove it. We're just going to play with it and see that it's true by experimentation. Same thing happens with the mean of all the p-hats. If you're doing proportions, the reason this is another common one that's done is that it happens to match the population proportion, which means that p-hat, the sample proportion, is an unbiased estimator of p. And remember, p-hat is the sample proportion, p is the population proportion, like the percent of people who are left-handed or whatever it is that you're doing. And the mean of all those sample statistics equals the population mean, which is why it's unbiased. Some would be higher, some would be lower, but they average out to be the same as the population mean. So naturally unbiased estimators are a valuable thing, and that's why these are the two most common that we're going to study a lot. In fact, most of the rest of the year is working with these two, X bar and P, and using them as estimators because they're unbiased as long as you do a random sample. So that's all we're going to do on that for right now, and we're going to talk about spread next. So spread has to do with how much does that statistic, X bar or p-hat or whatever, vary above and below its mean. So let's write that in a sentence. How much? How much does the statistic vary? And what generally happens with sampling distributions is that the spread of the sampling distribution, or the spread of the X bars or p-hats, is smaller than the spread of the individual values. So this tends to be smaller than the population spread. And that's another thing that I tried to show you in a warm-up, and I hope that that helped, that you saw it happening. I'm not going to prove it to you, but I am going to say that if you want the spread to get even smaller, if you want better and better estimates, what you do is you do bigger samples. If you do bigger samples, that gives you an even smaller spread. It makes your statistics even closer to the real value. That gives you a smaller spread of the sampling distribution. Which gives you even better estimates. And that's kind of a common sense thing. So let's think about means for just a minute. And I'm not going to try and draw this, I'm just going to say it. If you have, actually, you know what I'll do? I'll use yesterday's pictures. That would be better than drawing them again. So let's take these pictures that we drew on, technically this was Monday's second lesson. So we have our population. We take a sample from that population, and notice that that sample spread is usually a little bit smaller than the population spread anyway, and the mean of that is not going to be way out there on the outside. It's just not. The mean of a sample, I mean, maybe you might get 5 sample values way over here and have a mean that's about maybe here, but you're very rarely going to have a mean all the way over there. So that means your means tend to not go that far out. They tend to go a little bit further in. And the bigger your samples are, the further in they're going to go. The less spread there's going to be in this sampling distribution. So that's just a little sidetrack to say it makes sense that it would work that way. And I'm trying to, with the Desmos things, show you that as many times as I can so that you'll be convinced. I'm not going to do a proof on it because that's too much for high school. But spread tends to be less than the population spread, and it gets even smaller if you do bigger samples. So like a sample of size 1, that is the population, right? Just lots and lots of samples of size 1, but you want to get a bigger sample than that. So we are going to illustrate this by drawing 4 targets. Draw me 4 circles. Add some rings to make them look like targets. And we're going to do an illustration with darts or arrows, or imagine shooting darts at these targets for just a minute. And I want to talk about 4 possible situations that could happen, and I'll use the targets as those illustrations. So are you ready? I hope so. The first archer or dart player or whatever shoots darts that do this. So that's an interesting problem to have. This person, if you're giving them advice or coaching, you're going to tell them that they're aiming too high and to the right, and they just need to adjust their aim further down and to the left. They have a very small spread in their results, I guess I should say. They have a low variability, which is good. Good job. But they have a very high bias. Variability and bias are the 2 bad things you want to avoid. They are the opposite of variability is the opposite of precision, and bias is the opposite of accuracy. So this person is very precise, but not very accurate. They have a problem with the center of where they're aiming. So actually, that's not such a bad problem, and you could adjust the center a little bit, and this would be an easy person to coach, right? You just tell them to go down and to the right a little more. What about this person? Oh my goodness, they're all over the place. So let's think about their variability versus precision. Are they precise? No, they have high variability. They're all over the place. But I do see something good about this person's ability. Do you see it? High variability is bad, but there's something good about them. And that is that if you take the average of all of these shots, the average is pretty much in the center. So they are sometimes too far to the right, sometimes too far to the left, sometimes too high, sometimes too low, but they balance out so that the middle of their shots is the same as the middle of the target. That's low bias. Good job. They just need to work on their accuracy, or their precision, I should say. They've got decent accuracy in that they are not tending to go one direction or the other, but they need to work on getting those shots closer together and more consistent. Consistency is probably what I should have said. So low bias means they have a high variability, means they have a problem with their spread, but not their center. All right, imagine somebody who has both problems. They have high both bad things, both high variability and high bias. Do you know what that would look like? Draw it if you know it. If you draw it before me, I'll be so impressed. Actually, I won't know if you drew it before me. So this person I'm about to draw, they're all over the place, but they're also too far up and to the right. They're just, they've got a huge spread and they're not centering near the center. So they need to both pull it down and in, and they need to work on their consistency. They have both problems. Maybe a sad face for that person. That person needs a lot of help. Actually, that's probably how I would be shooting darts. It's kind of sad. And then it's possible to have neither problem, right? So we could have someone that is low variability and low bias, and that means that most of their shots are right around in here. Good job. This is the person who has neither problem. This is the best situation. They have low variability and low bias. Or they have high accuracy. They're very accurate and they're very precise. This is the best possible situation. So let's translate that into 4 graphs, because this is a 2-dimensional graph and what we really want is a 1-dimensional graph, because we're only working with one variable at a time right now. So we're going to draw 4 graphs. We're going to put mu in the middle of all of them. I would recommend you try to do this next part before I do it. So try to draw 4 graphs that have these same 4 situations. And this is how you can make sure you understood it. I recommend you pause the video and try that, and then come back and watch me finish. Okay, so this person has low variability and high bias. That means their estimates are all very close to each other. Let's go too low this time. So all very close to each other, but not centered around the mean. And that happens with some types of statistics. So we talked about how maximum is not a good estimate of the German tank total population. It always tends to be too low, but it is pretty clustered in one area, so that's good. High variability, low bias. What that looks like is all spread out, but also centered around the mean. And this is something we can do something about, which we will learn later in the chapter, what we could do about this. This is also something, both of these are problems we can work on fixing, and I'll show you how as we go through the chapter. Here's a person with high variability and high bias. Maybe they're really spread out and maybe a few of them are above the mean, but a lot of them are below. So high variability, high bias is bad. We could work on fixing that, of course, but then what we really want is centered around the mean and clustered all in one place. So that are the 4 situations, and we will be working this chapter on what would help us control this problem and make it more like that, and what would help us control this problem. Actually, controlling this problem is partially just choosing a good unbiased estimator like X bar or P hat, and partially making sure your sample is a random sample. So both problems are fixable in statistics, and we will be working with that all chapter long. All right, that is the end of lesson 7.1. Thursday, we will do a review warm-up and then notes on 7.2a and then the quiz on 7.1. So that's the plan.